like I said, we took a test last class, right, which is all about differentiation, but really with a huge focus on analyzing graphs and making the connections between the graphs of f, f prime, and f double prime. But one of the last derivative rules that we covered before we really sort of shifted gears and started looking at graphs was the chain rule. That was really the last major derivative rule that we covered. But there are plenty more, and in this unit, we're going to learn quite a few more. Okay, yeah, there's more to come. But today, we're not going to get into any new derivative rules yet. But what we're going to learn about is how to implicitly differentiate. And so let me kind of try to explain what that means. So all the differentiation we've done so far has been what we call explicit differentiation. And what I mean by that is that all the equations that we've differentiated have all been functions that typically we call y in terms of x. In other words, the y or the f of x is totally isolated. Right? So like, for example, if we wanted to find an equation that represents the slope of the parent quadratic function, we know how to do this, yeah? But I'm going to show the work a little bit differently, okay? Now, you already know what the answer is going to be here. Like, what's the derivative of x squared? 2x, right. So but I'm going to show this work a little bit differently in that what I'm going to do is use Leibniz notation. Instead, I've used Lagrange notation quite a bit, which is the y prime with a little apostrophe. Kind of have been leaving Leibniz notation behind, but we're going to bring it back today. Okay, so here's what it should look like. So if I want to differentiate this with respect to x, I'm going to say, okay, well, the derivative with respect to x of y should equal the derivative with respect to x of x squared. Right? So basically, we're differentiating both sides of the equation in terms of x. Now, the derivative of y, we kind of just took this for granted, I think, up until today, was just y prime, or the derivative of y with respect to x. Right? We can write that as either y prime or dy dx. So I think that's a step we really haven't focused on. We just sort of did it, and most of the time we wrote y prime. But then we can differentiate the right-hand side with respect to x, and we know what that derivative is. It's 2x. So basically what we've generated here is an equation that describes the slope of x squared at any point. Right? At any x value, we can plug in that x value and know what the slope of x squared is. And so this is the derivative of y with respect to x. So we already know how to do this, right? But you may be aware that not all equations have the y isolated. Okay? In some cases, you can have an equation where y is not a function of x, where you have multiple outputs for any input. So let me show you an example of that. Let's think about this equation. X squared plus y squared equals 1. Okay, and let's say I want to find an equation to represent the slope of that graph at any point. So before we actually try to find that, I want you to think about what does the graph of this equation look like? X squared plus y squared equals 1. And it should be, once you see it, a little familiar. Give me an example of a point that could satisfy this equation, like an xy coordinate point. So maybe we should plot this out so you can start to see what this is. Yeah, what would be an example of an x and a combination of x and y that would make that true? 0 and 1. Yeah, 0 and 1. 0, 1 should work, right? 0 squared plus 1 squared. Yeah, should work. What about what's another point that might work? 0, 1. Right, like 0 squared plus 1 squared works. Yeah. What else works?
1, 0.
Yeah, 1, 0. Okay, that works too. Very good. Yeah, 1 squared plus 0 squared. Oh, wait, that's the one I already plotted. Yeah, oops. Yeah, 0, 1, and 1, 0. Is there anything else you can think of that might work? Oh yeah, -1 and 0, right? -1 comma 0, because -1 squared would be 1. So we've got this point out here. Anything else? 0, -1. Yeah, good. Okay, so the graph is like starting to come into shape here. Anything else you might be able to come up with? I think those four are the most obvious ones. But there's quite a few other points that I think once I start listing them out, you'll start to recognize. Okay. Well, how about like, yeah, some of you are already starting to see it. Yeah. How about like √3/2, comma 1/2? Does that sound familiar to anyone? √3/2 squared plus 1/2 squared equals 1. Okay. Anything else? Now that you see that point, can you think of any other points? -1/2, comma √3/2 would be like somewhere up here. Good. Yeah. What else? √2/2, comma √2. What? Okay. So now you're starting to see what's going on here. Where are all these points coming from? I mean, we're not just like randomly coming up with square root points. The unit circle. Yeah. This equation is the unit circle. That's the unit circle. Right? Cosine squared plus sine squared always equals 1. Okay, so all of the points on the unit circle would satisfy this equation. And before you get too scared and like you're getting like flashbacks from pre-calculus at this point, don't be too worried. We're not going to really get into all of that. Okay, I just want you to think about like what this graph looks like. So we know it's just basically a circle of radius 1 that's centered at the origin. Okay, now we don't need to get too deep into this, but any equation that's in this form, x squared plus y squared equals r squared, is a circle that has a radius of r. So this would be a circle centered at the origin that has a radius of 1. Okay, so enough backstory there. I'm going to erase all this. We don't need any of this. Okay. Now, before we found an equation, let me go back up to the one we're talking about before, of y equals x squared. I'm going to draw that over here. All right, so we've got a nice little parabola. What is the slope when x equals 0? 0, and we can see that from the graph, right? We've got a horizontal tangent line, but we can also see that from the equation, because 2 times 0 is 0. Okay, what's the slope when x is 1? 2. Okay, because 2 times 1 is 2, etc. Okay, so we can see where we're coming up with these slopes. Now, if we look at a circle, we have a little bit of like extra challenge here, because if I say, oh, what's the slope of this graph when x equals, say, 1/2? And we're looking at this and we say, okay, 1/2 is like roughly here, right? So what's the slope when x is 1/2? I know you don't know the answer quite yet, but we have a little bit of a problem because y is not a function of x. So there's actually more than one answer here, right? Because the slope is going to be negative if we look at the line tangent to the circle when y is positive. But when y is negative, we have a different slope. We've got a positive slope. Yeah. So when you have an equation that's not a function and you want to ask the question like, what is the slope when? Instead of just being given x, I'm also going to have to give you y and say, okay, well, tell me the slope when x is 1/2 and y is √3/2. And then we'll find this slope. Versus like, what's the slope when x is 1/2 and y is negative √3/2? Okay, now finding that slope is going to require that we find the derivative of y with respect to x. dy dx is the slope of this function. This is not not this function, but this equation. So let's talk about how we find that. Yeah, how do we find dy dx if y is not isolated? And that's what implicit differentiation is. Okay, that's the difference between explicit differentiation, when y is defined explicitly in terms of x, versus implicit differentiation, which is where y is not isolated. All right, so let's go through the algebra and just kind of show how this works. Now, just like how we differentiated this up with the d dx on both sides, we're going to do kind of the same thing with this other equation. So we're going to say, take the derivative of both sides of this equation with respect to x. So d dx, okay, the derivative with respect to x of x squared plus y squared and 1. Okay, sorry for the interruption there. So we need to differentiate both sides. Now, the right-hand side, I think you'll find is a little bit easier to differentiate. What's the derivative of 1? 0. Yeah, the derivative of any constant is going to be 0. So we know what's going to happen on the right-hand side here. But I think the left-hand side is a little more unknown. Like, okay, well, how are we going to differentiate this with the y squared in there? That's what's kind of causing the problem. Okay, so when you have an algebraic expression here, like where we're just adding and subtracting terms, we can actually split up this derivative and take the derivative of each term individually, just like we did before, right? Like if you had a polynomial and I said, find the derivative of this polynomial, you would just usually use power rule on each term individually, right? So that's kind of what we're going to do here. We're going to split up this derivative and say that this is d dx of x squared plus d dx of y squared. Now, what's the derivative of x squared? You already know this. With respect to x, you just use power rule. It's 2x. The new part is going to be, how do we evaluate, or how do we find the derivative of y squared with respect to x? Because we're not differentiating with respect to y, we're still differentiating with respect to x. So we need to treat y not as though that's our independent variable, like we're doing x over here, but rather what it is, which is a function. So we need to treat y like it's a function. In other words, like, what's the derivative of, and maybe I'll write this out to the side. Well, hold on here. Let's say I want, what's the derivative of, of f of x squared? How do I find the derivative of this? Let's say this was on your test. Yeah? Oh, find the derivative of f of x squared with respect to x.
Do a square root to both sides.
Square root to both sides. We're not solving anything. We're just differentiating. Yeah. Okay, so we'll use power rule as part of it, but that's not all we'll do. We have to use chain rule, right? And find the derivative of what's inside. Okay, so what's the derivative of f of x? Well, it's f prime x, right? Right, so we're using chain rule here essentially, where first the power rule, the outside function is something squared, and then the inside function is just f of x. So it'd be 2 times whatever is on the inside times the derivative of what's on the inside. Okay, just chain rule, just the way it was, in the last unit. So let's do that here. Okay, so we say plus, we're going to use chain rule, 2 times y, and it would be to the first power, but I'm not going to write first power. Part of the reason that we really want to avoid writing the first power is we don't want to confuse that with y prime. Okay, y to the first power looks a lot like y prime if you're just handwriting it. But we also need to multiply this by the derivative of y with respect to x, which is dy dx, like we saw up here. Okay, the derivative of y with respect to x is just dy dx. So times dy dx. Now, the equation that's going to give us the slope of this is the dy dx. So ultimately, that's what you're going to try to solve for. So we're going to do that algebraically. We're going to use properties of equality and try to isolate the dy dx. That's the little term that we're trying to solve for. That's going to give us the equation for the slope. Because remember, the derivative of y is the slope of y. So this is just going to take a couple little algebraic steps here, but we want to get dy dx by itself. So we're going to subtract 2x, and then we're going to divide by 2y. So first I'll subtract 2x from both sides. And then divide both sides by 2y. So I get dy dx equals 2 divided by 2 would be 1. So negative x over y. So now you can see that we are going to get a different slope if we give you a positive y value versus a negative y value, because now our derivative is not only in terms of x, but it's in terms of x and y. Any questions so far? Okay, so let's take, oh, yeah, question or no? Yeah.
I understand like taking the derivative of it and like the 2x and the 2y, but why did you multiply it by dy dx at the end? What was the code?
Oh, yes. What we did here was we used the chain rule. Okay, so imagine I had some other function, like y is just a generic function, right? Like just forget about what y is for the moment. Let me give you a different function. Okay, let's say my function was cosine x, or no, let me give you an easier one, sine x. Let's say I want the derivative of sine squared x. Talk me through the process. How would I do that?
I would do 2 times sine x times cosine x.
Very good. What is cosine x in this context?
The derivative
Of what?
sine.
Right. So we have, in this case, 2 times y times the derivative of y. In this case, the derivative of sine. But in this case, we don't know what y is, right? It's just an equation, an expression. So it's just dy dx. The derivative of y is the slope of y. Yeah. So it's just the sort of algebraic magic that's happening here is the chain rule. But
You don't have to do that one for x, so.
no, because we're differentiating with respect to x.
Okay.
Yeah, so that makes a big difference. Hello, good morning. Yeah, good question. Okay. So the next question is to find an equation of the line tangent to this curve at root 3 over 2, comma 1/2. Okay, so this formula that we just found, that's this formula that we're going to use for the slope. If we want to write the equation of a line tangent, we've worked out, probably hundreds of these kind of problems. What's our setup here? What are the things that we need to find? Yeah. Okay, so we need to find the point, right? A slope. And we're going to write this equation in y minus y1 equals m times x minus x1 form. So for this problem, what's the point that they're asking us to find the equation of the line tangent to? Root 3 over 2, 1/2, right? It's given. Now, usually, like in all the problems before this, except for that one point of inflection problem, they all gave us what x was, right? But as we saw earlier, when we're dealing with relations that are not functions in terms of x, we're going to have to be given a y, right? We said earlier, like if we're given an x value of 1/2 here, the slope is going to be different whether we're given this y or this y. So yeah, so we're given both the x and the y here, which is kind of nice. So root 3 over 2, comma 1/2. And then we need to find the slope. Now, we already did kind of the hard work there, right? We found the slope was negative x over y. So the slope, our m, will be negative root 3 over 2 divided by 1/2. Very good. Yeah, so it's negative root 3.
Oh, sorry.
Yeah. So now we've got all the pieces that we need. We've got our x, we've got our y, we've got our m. So we can go ahead and write our equation. So y minus 1/2 equals negative root 3 times x minus root 3 over 2. Now, just to kind of pull this back to the picture that we drew earlier, so you can kind of see what we're talking about. This point, root 3 comma 2, root 3 over 2 comma 1/2, is roughly this point right here, right? It's that point on the unit circle, where theta is 30 degrees, pi over 6. And the equation, or the line that we just found the equation to, is this line right here. Okay, the point is root 3 over 2 comma 1/2, and the slope is negative root 3. In other words, it's going down root 3 over 1. Yes, ma'am?
Did you find the slope again?
Okay, so the slope we got from this equation that we found in the previous part. So this is where the implicit differentiation comes in. When we differentiate both of these sides of the equation with respect to x, we're going to have to use chain rule on the y squared. Okay, we kind of went through all that. But this dy dx, that's the slope. Okay, and that's what it's always been. It's just that previously, y was isolated. So we really didn't give much thought to like that object being like being able to be manipulated algebraically, right? But here, we're going to see that that's going to turn up like somewhere in the middle of the problem, and we're going to have to isolate that out. And then once we do, we've got an expression for now we can find the slope at any point. Yeah. Yeah, good question. Any other questions? Okay, so that's the big idea behind implicit differentiation. Now we're just going to do some practice problems, okay? So look at this crazy equation, okay? We got 3x squared y plus xy cubed equals sine y. Okay, I wouldn't expect that you know what this looks like, but I threw it into Desmos just so you could see what this weird graph looks like, and look at that. That's what it looks like. Okay? Yeah. Would not expect you to graph that or anything. But what we want to do is come up with an equation for the slope of this equation. Well, yeah, what does it look like it is at x equals 3? 0. It kind of looks like it's 0. So you could be wrong. It might be like slightly sloped there, right? Maybe it's just like you can't tell. But what would be a good way to check is if we do this right, if we plug in 3 comma 0, we should get 0, or at least something close to it, right? So that'll be a good way to see if we're doing it right. I believe it is. I believe it is. But we can check. I mean, basically what this is saying is that if y is 0, or there will be an infinite number of points, like no matter what x is, y could be 0. Yeah, but remember, y is not a function of x here. So given an x value, we might have multiple y values. Solving it algebraically is not really going to be our goal here. I don't even think we can do that at this point, or really like even at the end of the year, you won't be able to. Like isolate y in this equation is what I mean. Okay, so y'all ready for this implicit differentiation? Let's see if we can handle it, okay? So we're going to do dy dx on both sides. Okay, so I'm sorry, not dy dx, just d dx. We're going to find the derivative with respect to x of 3x squared y. And if it's not too much, I think I'm going to just split it up front here. Okay, split up the expression and say plus d dx of xy cubed equals d dx. So we're basically taking the derivative of both sides with respect to x. Okay, so what you sort of have to keep track here is that we're differentiating with respect to x. So anytime you see y as part of this derivative, we're going to treat that like it's a function and differentiate it like we did functions, like that we've done functions this whole year. And so when we see something like 3x squared times y, think of this as like 3x squared times f of x. And then how you would approach that differentiation is how you're going to approach this. Right? Like if y was just some other function, like cosine or e to the x or 2x squared, what rule am I going to need to use here if it's 3x squared times that function? Product rule. Exactly. So we've got to use the product rule here on this piece. We're also going to have to use the product rule here. And actually a little chain rule. We won't really need chain rule over on the first one. Over here, no product rule, obviously. It's not a product, but we will need to use chain rule. So basically that y, as you're thinking about how to differentiate it, you want to think of it as a function. And differentiate it as though it's just like, g of x, or just like some other unknown function. Okay, so let's see if we can differentiate this. So we're going to use the product rule, okay, just as a little reminder. Oops. Product rule goes like this. If I want to differentiate f times g, it's going to be f prime g plus fg prime. All right, so in this case, the f is the 3x squared and the g is the y. All right, so f prime, what's the derivative of 3x squared? This should be like automatic, 6x, okay, times the g, which in this case is just y. All right, so that's the f prime g plus fg prime, so plus 3x squared. Now what's the g prime in this case? What's the derivative of y with respect to x? dy dx. Okay, the derivative of x with respect to x is 1. The derivative of y with respect to x is dy dx. One way to keep that straight is like if, even though like, at the risk of you starting to think of this like a fraction, which is a great risk, this is not a fraction, but if you differentiate x with respect to x, anything divided by itself is 1. Yeah, so the derivative of x with respect to x is 1. Okay, yeah, just a little trick there. Help you think about that. Okay, so this is the derivative of 3x squared y with respect to x. Now we're going to differentiate with respect to x times y cubed. We're going to have to use product rule again, where in this case our f is x and our g is y cubed. Another product rule here. Plus the derivative of x with respect to x. Okay, that's 1. Times the derivative of y cubed. The what? Oh, you're right. Yeah, times y cubed. Yes. Sorry. Okay, plus Just getting a little ahead of myself. F, which is x, times, now we'll do the derivative of y cubed with respect to x. So we're going to treat y like it's a function, and we're going to have to use chain rule. So 3y squared times the derivative of y, which is dy dx. Okay, so now we've got the whole left side differentiated. Now we've got to differentiate the right side. This is going to be another instance of the chain rule. This chain rule is going to be like all over the place in this unit. So hopefully you got that down. Yeah. All right, let's differentiate sine y. Okay, so what's the derivative of sine? Okay, so we have cosine of y times the derivative of the inside, so times the derivative of y, which is dy dx.
Can you divide the whole thing by dy over dx, or does it not work?
Well, that's what we're trying to solve for. That's what we're going to try to isolate. So you kind of want to do actually the opposite of that. Besides, not every term has one. Yeah. So it can be pretty easy to get overwhelmed with this expression, or this equation, rather. There's a lot going on with this equation. But let's stay focused on like what it is we're trying to isolate here, and that is the dy dx. We're trying to get this thing by itself. All right, so this is where the algebra, you really got to pay attention to what you're doing here. Okay, here's this. You're going to do these same two steps on all of these problems. Okay, the first step is going to be to move all of the terms that have the dy dx to one side, and all of the terms that don't to the other side. Okay, so let me underline all the terms here. 6xy is a term. 3x squared dy dx is a term. Y cubed is a term. Okay, so I'm basically everything that's separated by pluses and minuses. So what I'm going to do is I'm going to collect all of the terms that have dy dx on the left side, and then I'm going to collect all the terms that don't on the right side. So like this one's going to stay on the left, right? This one's going to stay on the left. This one I need to move to the left, right? And then all the terms that don't have dy dx, I'm going to move to the right. So I'm going to move this one to the right. I'm going to move this one to the right. All right. Okay, so the ones that should be on the left are this one, and this one. So I'm going to start by writing the ones that are already there. Okay, so 3x squared. Oops, let's clean that up a little bit. You know, this is where making sure you're writing neatly is really important. You know, when these equations start getting really long, if you're all over the page, it's going to be really easy to lose track of what you're doing. So just, you know, take your time. There's no rush here. Okay, so those are the two terms that were already to the left. But now I'm going to bring that one that has a cosine y over to the left. Minus cosine y, dy dx. All right, so those are all three terms that have the dy dx. And now all the terms that don't are going to get sent to the right side. Okay, so minus y cubed, or actually let me start with the 6xy because that's the first one that shows up. Negative 6xy minus y cubed. All right, so these are the two terms that did not have the dy dx. Any questions so far? Yeah, we're about halfway done. Yeah. Okay, maybe more than halfway. All right. Does anyone see what our next two, like what we need to do next, or not really? Like how are we going to get the
terms?
Combine like terms? Exactly. Now, it's going to look like pretty crazy to combine like terms here, but there's a way to think about it a little differently. Instead of, now, if this is technically combining like terms. I'm actually kind of happy you said that, but because most people will not see it that way, but that is true. But another way to think about it is we're going to factor out the dy dx as a GCF, as a greatest common factor. Like just pull that out like you're doing distributive property, but in reverse. That's why we're collecting them all on the same side, so that we can do that. All right, so we're gonna like pull out this dy dx, this dy dx, this dy dx, and bring them all out to the front. So dy dx times everything else. Okay, so we like factored out that dy dx. Oops. Out of the whole expression. The right-hand side will just remain the way it is. Thank you. Yeah. Okay, we're almost there. There's only one step left. How am I going to isolate dy dx here?
Divide by 3x squared plus x squared.
That's exactly right. It's just dy dx times all that stuff. So what we need to do is just divide both sides by that huge expression. No, remember, like on these, you do not have to simplify. I don't even think you could. I don't even think you could. So dy dx will equal negative 6xy minus y cubed all over 3x squared. I'm actually going to rewrite this next term just ever so slightly and pull that coefficient of 3 out to the front. So it looks a little bit more like what we're used to seeing. So plus, I'm not really simplifying anything. I'm just rewriting it slightly so that it looks a little better. You know what? I'm not even going to bother with the parentheses around the y here. I don't think it's just too much. And there's your equation for the slope. This equation will find the slope at any point on that graph. So if I want to find the slope at 3, 0, if I look back at that graph, it kind of looks like the slope is 0 at 3, 0. And so what I would expect is if I plug in 3, 0, is to get 0. And you can see right away that that's going to happen because if the y coordinate is 0, this is just going to equal 0 divided by something is 0.
Calculators on the test.
What did we need a calculator for? We did like no arithmetic. In fact,
I meant like if we actually like plug in stuff. Take a lot of space to write.
it would be, I would make sure that the points picked strategically.
Okay.
I mean, really, because of the cosine y here, I can't go too crazy.
So if you plug in, what happens when you plug in x?
X and Y.
I'm asking about the points.
Yeah, you need a point for x and y to say, okay, what is the slope at this point? Right, so 3, 0, this is going to simplify to be 0 because if y is 0, then this is just going to be 0 over something. You're right. In fact, that means that we absolutely assuredly have a horizontal line at 0 because if y is 0, this whole thing's going to be 0 no matter what x is. Yeah. I'll let this sink in. Yeah. Okay, let's summarize this process. How did we get there? Okay, we started with this equation. How do we get here? Let's break it down. First, you're going to differentiate each term. Okay. Remember, and maybe I'll make a little note out to the side here, that the derivative of y with respect to x is dy dx. you're going to treat y like it's a function. Most of the time, you're going to have to use chain rule. Okay? If there's anything besides just y, like if it's like 2y or y squared or the square root of y or anything like that, you're going to have to use chain rule. Okay, so differentiate each term. Then you're going to move all the terms, all the dy dx terms to one side. Okay, like we did here, we identified the terms that had the dy dx. We brought them all to one side. Then you're going to factor out dy dx as a GCF. I can zoom in here now that we're to that point. So that's what we did up here at the top, is we factored out that dy dx. And then finally, you're going to divide. Okay, you're going to divide by whatever's in the parentheses to isolate dy dx. This is going to take some practice, for sure. I mean, I think the easy part, easy in quotes here, easier part, is just understanding the calculus of what we're doing. Okay, the hard part is the algebra. And that's going to be kind of a common theme this year, where the calculus is a lot easier than the algebra is.
Yeah, I was like, this is annoying algebra.
That is sort of that's the hard part of calculus, is making sure your algebra is on point. Yeah. There is a calculator portion, but we didn't need a calculator here like we didn't know arithmetic. We didn't add or subtract or divide or multiply anything.
It's still nice for the auto.
Will it auto do it for you?
For if you have points.
It'll differentiate for you? And it'll give you the actual equation.
No, it only give you
like a point, right? Yeah. Okay. Any questions so far? We got one more example for you. It says find the equation of the line tangent to this wacky equation at 1, 3. So take a look at this graph. Okay, here's the graph of this equation. Now, I'm just throwing the graphs up here so you can kind of put a visual to it, but you don't need to know what these graphs look like. I'm not, this is not going to be a calculator test or anything. But I just want you to kind of like get a visual for what it is we're actually doing. We're trying to find the line tangent to this curve at 1, 3. So at this point right here, there's a tangent line, right? We're trying to find the equation of that line. So to find the equation of that line, we need the same two things we've needed since Unit 2 to write an equation of a tangent line: point, a slope, and then plug it into point-slope form. So we need a point, and we need a slope. We'll plug that into y minus y1 equals m times x minus x1. The template here is the same. We're going to be solving this same exact problem all year long until everyone gets it right. All right. Yeah.
including me.
Including you, yep. Need 100% accuracy on these tangent line problems. All right, so the point, what's kind of nice here is, before we had to figure out what the y coordinate was of the point typically. Here it's given. Okay, the point is going to be 1, 3. All right, that's, again, that point that we see over here. The slope is the hard part, because we need to figure out, in order to find the slope, we need to plug in 1, 3 into the slope equation, into our dy dx. This is where the implicit differentiation comes in, because we're going to have to implicitly differentiate this equation, solve for dy dx, then we'll have an equation that we can plug 1, 3 into. All right, so let's find that slope equation. So d dx of x cubed y squared. So we're going to have to use product rule and chain rule. plus d dx of negative 5x, or I guess I could just say minus, might be an easier way to do that. Equals
I wish I could just do that with paper.
yeah, I know. D dx of y cubed minus d dx of 23. Yeah.
What is d over dx stand for? Is that just like the derivative?
Right, that's exactly what it stands for. The derivative with respect to x. Previously, and even still now, oftentimes, and in fact more often, we use the other notation with the dash. That's what it means. Y prime is dy dx.
But the dy over dx is the derivative of y.
Specifically y. Exactly. Yeah, because you could differentiate anything you want. Yeah, like in this case, we're differentiating all these different expressions as opposed to just y. Now we're going to find the dy dx in there, but we are differentiating the whole expression. Okay, these are just two different notations. We've got the Leibniz notation, which is the dy dx, and the Lagrange notation, y prime. But they both mean the same thing. It's two different mathematicians have their own ways of doing things. They both have pros and cons. The really nice thing about the d dx is it tells you, or it indicates what you're differentiating with respect to, where the prime doesn't. Now, in calculus AB, calculus 1, it doesn't really matter because you're only ever differentiating with respect to the independent variable, like usually x or maybe sometimes t, right? But as you move forward in mathematics, you're going to find out like, hey, wait a minute, we can have an equation with any number of variables, right? Like what if we're trying to model something in 3 dimensions? You have x, y, and z. Well, do we want to find the rate of change of how it's changing in the x dimension and the y dimension or the z dimension? And so you might differentiate with respect to these different variables. And so this notation allows you to say what you're doing. Yeah, you say, okay, I'm differentiating with respect to x or with respect to y or z. Now in this class, introductory calculus, we're only really going to be doing it in terms of x. Maybe t if we're doing like a position velocity question. Okay, so let's go through the algebra here. We got this. Let me just move this over a little bit more. Okay, so we're going to have to use product rule on that first one. So derivative of x cubed with respect to x is 3x squared times y squared plus x cubed times the derivative of y squared. This is the hard part. This is the new stuff, right? 2y times dy dx. Good. So that's going to be like one of our terms that we're going to like pull. So maybe I'll do a little underline here to like just keep track of that as I go. Okay, so that's because I'm going to solve for dy dx, and the strategy here is once I do all the differentiation is to move the terms that have dy dx over to the left. So I'm just underlining so that on the next step I can just point and be like, okay, I need that one and that one and that one to the left. So I'm differentiating y with respect to x. So I'm using chain rule essentially. Yeah. All right, what's the derivative of 5x with respect to x? 5, okay. So now the left side's done. Now I'll do the right side. What's the derivative of y cubed with respect to x? 3y squared, so we've got to do power rule, times dy dx, the derivative of y with respect to x. Thing is, we don't know what dy dx is yet. That's what we're trying to find. Minus 0, yeah. Because 23 is a constant. All right, so we've got two terms that have dy dx. We're going to isolate those by doing those two last steps. We're going to subtract those or move those to the left, move everything else to the right. factor out the dy dx as a GCF, and then divide. And then we should have our slope equation. All right, so I've got x cubed. And I'm actually going to bring that 2 out to the front just to make this look a little nicer. 2x cubed y dy dx. Okay, that's that one. Minus 3y squared dy dx. Okay, that's that other one over here. Equals negative 3x squared y squared plus 5. Okay, so I pulled the 3x squared y squared minus 5 over to the right-hand side using those properties of equality. I subtracted the 3x squared y squared from both sides, and then added 5 to both sides to do that. Exactly. Now we're going to do the GCF thing, right? I'm going to pull out the dy dx as though it's the greatest common factor, which it is. I would highly advise you do. Yeah, I mean, just in general, the more work you show, the less opportunity you have for an error. You're not doing everything in your head. Okay, now our last step here is going to be to divide everything that's in the parentheses. So dy dx is going to be, a negative 3x squared y squared plus 5 over 2x cubed y minus 3y squared. Whew, all right. That's the equation that's going to give us the slope. We haven't actually found the slope yet. That's the general slope. That'll give me the slope at any point. But now I need to find the slope at a specific point. Now, the notation I'll use for that, I'll just kind of block this off here. Or before I do, I want to make sure we're all caught up. Any questions about the algebra that's been done here? Any steps that you want clarification on, or? Okay, so what we want to do is we want to evaluate dy dx when, or at the point, what was the point again? 1, 3. Okay, so this is just some notation that don't really use too often, but the way to read this, like there's like a bar here, is just dy dx at 1, 3. So I'm just going to plug in 1 and 3 into x and y, and hopefully I can handle this without a calculator. Fingers crossed. All right, so minus 3 times 1 squared times 3 squared plus 5 over 2 times 1 cubed times 3 minus 3 times 3 squared. So we're going to need to simplify all that, obviously. All right, it's not too bad, though. We've got 3 times, so negative 3 times 1 is just negative 3 times 9. Negative 3 times 9 is negative 27 plus 5, negative 22 up top. Double check my arithmetic here. Make sure we agree. Okay, and then at the denominator,
2 times 3 minus 27.
2 times 3 is 6, minus 27.
Negative 3.
Okay, so this would be positive 22 over 21. What does that represent? That 22 over 21, like what is that? That's the slope at that point. Right. It's positive. It's almost 1, actually, right? It's very close to 1. And you can even see on my crummy sketch that, it kind of looks like that slope maybe is pretty close to 1. We're just going like up 1 over 1. Not exactly, but pretty close. All right, so now we got the slope is 22 over 21. And so now we're ready to write our final answer here. Y minus 3 equals 22 over 21 times x minus 1. And that's how you differentiate implicitly. Yeah? Any questions?